the topic. And I think the same as Hans, I'm also very much looking to the questions that we will receive. So first of all, I would like to say thank you to ECI who enabled the study. Hans already mentioned that there is a part 1 of the paper that laid the theoretical foundation of the methods and principles for primary energy factors that we used for the second part. And finally, I'd like to also say thank you to my colleague Nation, who unfortunately can't join us today because she just got a baby, but I'm sure she also provided a lot of very interesting input and important input to the study. So it's also thanks to her that we can do this presentation today like it is. Okay, let's move on to the next slide, which gives you an overview about what we are going to do within the next 3/4 of an hour approximately. First of all, of course, there will be an introduction. I will briefly return to the definitions that were given in part 1 of the paper. Then we will have a look at what the different directives, the most relevant European directives tell us about primary energy factors. Then we go to review some of the primary energy targets, which are also included in some of the EU communications apart from the directives. And then we move on to the policy implications of different primary energy factor definitions, which is the core of the research we did here. And then, of course, it's interesting to see what we conclude from the findings of the previous steps. So the introduction is, well, what we are talking about here. Of course, everybody is aware that it has been common sense for several decades that we talk about primary energy factors, especially for non-renewable energy sources. And you have a further differentiation here between combustibles and non-combustibles. You have, for example, hard coal, lignite, natural gas, of course, and to the non-combustibles, nuclear energy is counted. But recently, as we see much more interest in renewables, and as we obviously have targets for increasing renewable energy, also for achieving the climate targets that we have, new sources, or of course they are not new, but they get much more emphasis, get into the focus, which as to combustibles again would be biomass, waste, the biogenic part of the waste, and again non-combustibles like hydro energy. It might come from run-of-river power plants, tidal plants, wave and ocean plants, wind energy, solar energy, which is photovoltaics and solar thermal, and geothermal energy. So that's what we are talking about, and the question is, where do we really see interpretations and differences in accounting for the primary energy for these different sources with a focus on the renewable energy sources? So going back to the definition, in the following, I'm using some of the results from the first part of the study that was written by PE International. This is one of them, and they cite here one of a typical primary energy definition from Professor Nakicenovic from 1996. It says, the energy that is embodied in resources as they exist in nature. The chemical energy embodied in fossil fuels or biomass, the potential energy of a water reservoir, the electromagnetic energy of solar radiation, and the energy released in nuclear reactions. Okay, this is one way to do it. And we will see this can be differentiated significantly when you deal with this topic a bit more in depth. So how is it usually calculated, the primary energy factor? What you can see here is that usually we have an output. This may be electricity or heat. And this is set into relation with the fuel that we have on the input side, which usually is calculated like, let's assume 1 kilogram of coal, and what is the calorific value of the coal. Then you have the total input in energy units, and you divide it by the output, and that's the primary energy factor. In principle, in many cases, and in the most easy cases, like for example electric power plants, let's assume that only produce electricity, this is simply the reciprocal value of the conversion efficiency. So this means this formula works very well for combustibles, regardless if they come from renewable sources or from non-renewable sources. But then, what Hans already mentioned, we have different accounting principles. Let's call them principles here, because later on we also talk about methods for the accounting, which are differentiated into 4 classes. Number 1 is called the zero equivalent solution, which means by definition we say all renewable energy sources simply get a primary energy value of 0. We won't go very deeply into this version of a definition, but of more interest relative to the directives and also to the national accounting, to the statistics, in the statistics is option number 2, which is about assigning primary energy equivalents to renewable energy sources. We will go deeper into that later on. The third method is only looking about the non-renewable share or the non-renewable energy, which is related to providing energy from renewable sources. We also don't go very deep into that because it's only about the non-renewable share. But much more interesting, again, is number 4. So there will also be a focus on number 4 in the following slides. This is about accounting for non-renewable and renewable primary energy, which means that total primary energy is split up into a non-renewable share and a renewable share. And again, the fossil primary share is looked upon, which, for example, is needed for infrastructure that we need to provide energy from renewable sources. Let's just imagine we have a biomass, wood. So in order to get the wood from the forest, you usually need tractors or diesel-driven engines of any kind, which are needed to get the wood to the sawmill. And this, in a full balance, also has to be taken into consideration, and that would be included in such a life cycle assessment balance. So the methods that we have in the first part of the paper are called the zero equivalent method, the direct equivalent method, the physical energy content method, the substitution method, and the technical conversion efficiencies. I will briefly relate to that. So the first one in principle I already mentioned. You simply say renewable energy, this is zero primary energy. Then you have the direct equivalent method. In this case you say, okay, if a renewable energy technology produces 1 kilowatt hour of heat, for example, this is equivalent to 1 kilowatt hour of primary energy heat. And the same would be true for electricity. When, for example, a PV system produces 1 kilowatt hour of electricity, you would account for that with 1 kilowatt hour of primary energy. So very easy approach so far, but it gets a bit more complicated when we go to the physical energy content method. This is based on the first step in the energy chain, which can be used directly. So a very good example is, for example, geothermal energy. Here you say the first useful source would be the heat that comes from the geothermal source. So the heat that comes from the ground would be 100%, and if we use the heat directly, we would say, okay, this is 1 kilowatt heat equivalent to 1 kilowatt primary energy. But if we do generate electricity from that heat with an efficiency of 10%, for example, then we would have to take the reciprocal value, which would be 10, a primary energy factor of 10 for electricity that comes from geothermal energy sources. Then we have the substitution method. That's also quite straightforward because it simply says, relative to electricity, that regardless which source we have, which renewable source we have, as long as it produces electricity, we simply say it has a primary energy factor of 2.5 because we compare it with a standard grid mix, which has an efficiency of 40%, and the reciprocal value would be 2.5. So we simply would say, okay, renewable energy electricity replaces conventional electricity, and therefore we assign the typical fossil efficiency and primary energy factor. Then the technical conversion efficiencies, again, is kind of straightforward. Here you really say we have some input into the renewable energy technology, and then we compare this input with the electrical output, and obviously we can have very different efficiencies, as you will see in the next slides. So here we have an example combining the principles I mentioned and the methods I mentioned. You see that, where's the arrow? I take the arrow. Here you find again the options, option 1, 2, 3, 4, and let's just have a look at option 2, which was about the primary energy equivalent, and option 4, which was about looking at the life cycle balance. So here you see for option 1, we can use 3 different methods for accounting. It's the direct equivalent method, the physical energy content method, and the substitution method I just explained. And here in option 4, which is about life cycle assessment, you see that we either use technical conversion efficiencies or, again, the physical energy content method, and that in option 4 we explicitly make a difference between the non-renewable share and the renewable share in primary energy. Just giving you an idea about the difference it makes at looking at either one or the other method, I highlighted wind energy, for example. Here you can see, assuming 1 kilowatt hour of electricity from wind, taking the physical energy content method would result in 1 kilowatt hour primary energy, while taking the substitution method with a typical 40% efficiency assumption would result in 2.5 kilowatt hours of primary energy. So the list is continued with other sources, geothermal, biomass, waste, and nuclear. Let's go back to give you the others explicitly. So you can see the sources that we analyzed. So we analyzed hydro energy, storage power stations, hydro energy from runoff river power stations, wind energy, solar photovoltaic, solar thermal electric, and then on the second page, geothermal, biomass, solid biomass, and biogas. And we also had a look on waste and nuclear energy efficiencies. So very big differences you especially can see in geothermal energy, and you see there is a range between 1.0, primary energy factor of 1.0, using the direct equivalent method, up to 10 using the physical energy content method. And so you can already imagine that using either one or the other method will have quite some impact on interpretation of data. So when you have a look at the energy balance of countries, it means that using one or the other method will of course also lead to very different primary energy factors for the grid mixes. So here in this example we took 3 different countries which have which use very different sources for producing electricity. So we have the grid mix of Norway, for example, which is largely based on hydro energy. And here you can see that then, taking the mix of all these sources, we have a total primary energy factor which is very close to the hydro energy factor that we've seen before. So it varies mainly between 1.2 and 1.9, and using option 4 it would be close to 1.25, 1.1, and imported energy is usually accounted for with 1.0 regardless from which sources this comes, which is also quite interesting. And on the second page, you see two more countries that we took as an example. It's the grid mix of Poland, which is largely based on fossil sources. So all these conversion efficiencies are very close to the conversion efficiencies of the power plants, which use fossil fuels. And then we have the grid mix of Spain, which is a mixture of fossil fuels and non-renewable, fossil fuels and renewable sources. And as we can expect, the values lie somewhere between Poland and Norway. But still, you can see there is quite a big range in the grid mix of Spain, 1.7 to 2.5, depending on the method that we use for calculating the primary energy factor of a country. So let's have a look on the directives that we analyzed. It's the Energy Efficiency Directive, the Renewable Energy Directive, and the Energy Performance of Buildings Directive. First, we look at the Energy Efficiency Directive, and the overarching target of the Energy Efficiency Directive is that it says we should achieve minus 20% in end-use energy between 2005 and 2020. Explicitly, Article 7 of the EED states, the amount of energy savings required or to be achieved by the policy measure are expressed in either final or primary energy consumption, using the conversion factors set out in Annex 4. When we go to Annex 4, we find a footnote 3 as to electricity, and it states for savings in kilowatt hours, electricity member states may apply a default coefficient of 2.5. Member states may apply a different coefficient provided they can justify it. So it means 2.5 may be used, but it's not mandatory as long as member states have a good reason to deviate from that and to take another primary energy factor. Interestingly, there is no explicit differentiation between primary energy factors for renewables and non-renewables, so it's about total primary energy and not just fossil primary energy, as we will see later in the Energy Performance of Buildings Directive. Then let's see what the Renewable Energy Directive says about primary energy factors. So summarizing this before I conclude, I would like to mention although primary energy factors are so important, all these directives say surprisingly little about how to deal and how to handle primary energy factors. So, but specifically the Renewable Energy Directive, it gives mandatory requirements on EU member states. It says the EU shall obtain 20% of total final energy consumption from renewable sources by 2020. The targets are distributed differently to the member states, and specifically to the factors the Renewable Energy Directive says, it is necessary to set transparent and unambiguous rules for calculating the share of energy from renewable sources and for defining those sources. It is proposed to use the calculation methods applied by Eurostat for primary energy factors. And again, no difference between primary energy factors for renewables and non-renewables is specifically mentioned. The Energy Performance of Buildings Directive is a bit different as to handling with only total primary energy or not. First of all, we find some words about primary energy factors in Annex 1 of the EPBD, which is the common general framework for the calculation of the energy performance of buildings that has to be applied in national regulation by all member states. It says the energy performance of a building shall be expressed in a transparent manner and shall include an energy performance indicator and a numeric indicator of primary energy use based on primary energy factors per energy carrier, which may be based on national or regional annual weighted averages or a specific value for on-site production. It means the values may be based on these factors, but they also can be on average factors, on EU factors, 2.5 for example for electricity, but again, if a member state has a good reason to deviate from this 2.5 for electricity, it may do so. Then we have two conventions related to the EPBD. There is a big set of CN standards around the European Performance of Buildings Directive and the standard dealing with the energy performance for dealing with calculation of the energy performance of buildings balance is EN 15603. It's the standard called Energy Performance of Buildings, Overall Energy Use and Definition of Energy Ratings. It says national annexes may be added to the standard, giving tables of values representing local conditions for electricity generation and fuel supply. Such tables shall give values for primary energy factors or non-renewable primary energy factors, depending on which are to be used at national level. This means, in contrast to the other two directives, not only total primary energy factors or total primary energy use is spoken of, but it's explicitly mentioned that we could have a difference between total primary energy factor, or we also could only look at the non-renewable part of the primary energy of the primary energy use by only applying non-renewable primary energy factors. This difference is important in calculating the primary energy demand of a building, and it's a very easy formula. You can see it's two terms here. On the sum on the left is in principle the imported energy, the electricity delivered to the building in this case when looking at electricity, and the right term deals with the exported energy. That means on-site energy or nearby produced energy that is exported from the building. And obviously the total balance or the result of this equation is largely determined by the primary energy factors that we find in this formula. Here you can see the primary energy factors for the imported energies. It means the energy that is delivered to the building, and here you see the primary energy that is exported from the building into the grid. And obviously we intend to get very low primary energy values for buildings, and depending on how these factors are specified, the result will vary significantly. It is also interesting that the EPBD or the standard EN 15603 explicitly mentions that these two factors for imported and exported electricity may be the same, but also different values could be used if they are available and realistically or reasonably based. So having a look at the targets, we have an EU communication, the Action Plan for Energy Efficiency. It is older than the Energy Efficiency Directive, and it was the first document, I think, that mentioned the 20% energy efficiency target. We have, which means 20% energy savings relative to a fixed baseline projection. But very interesting in this context is that how would the directive like to achieve these 20% energy savings? So it mainly should be achieved by increased end-use energy efficiency, and secondly also by improved conversion efficiency on the supply side. So also the supply side is included, but mainly the 20% should be realized on the demand side. That means reducing final energy use. As you know, probably, we have the 20-20-20 by 2020 targets. These 20% that you can see here is one of them. We have 20% share of renewables, 20% energy efficiency improvement, and 20% reduction of greenhouse gas emissions. And specifically, this target here of increasing the energy efficiency by 20% is not on track. So currently, it seems that only half of it will be realized by 2020. And so, again, as the statistics tell us, if we are on track or not relative to energy efficiency, it is very important how primary energy factors of renewables and non-renewables are determined to create a energy balance that tells us if we are on track with these targets or not. Then we have the energy roadmap. It also tells us that very significant final energy savings are needed, which explicitly means that the primary energy use reduction should also be based on a significant reduction of the final energy savings, of the final energy use, and not just by decarbonization of the electricity supply. So this is an overview of primary energy statistics which are used. So let's again only have a look at the principles or the options 2 and 4. It's interesting that statistics worldwide not at all use the same approach. So we have sub-option 2A, for example. It's used in UN statistics. It's the direct equivalent method. Then we have the physical energy content method. This is used by the International Energy Agency, by Eurostat and the OECD. And finally, the substitution method is used in the statistics by the US Energy Information Administration. Life cycle assessment so far is not used in energy statistics, but still gives us a lot of insight in what the application of such a method would mean in energy statistics and in determining how far we are with the different targets we have in the directives in Europe. Again, as a reminder, to refresh your memory, we just said, let's go back to Europe. Europe is using the method 2B, so Eurostat. And this is the physical energy content method, which, for example, for wind would use a primary energy factor of 1.0 and for geothermal of 10. So now let's have a look at the policy implications on the 3 directives I just mentioned, the Energy Efficiency Directive, the Renewable Energy Directive, and the Energy Performance of Buildings Directive. We start with the Energy Efficiency Directive, and in order to make it transparent and a bit more illustrative, we use an example. Imagine we have a country without nuclear energy, and this country achieves 10% savings in final electricity use. Then let's assume that 50% of the energy system or 50% of the electricity comes from fossil power plants, and the other 50% of the electricity production is based on renewable energy. As you have seen, we are dealing with different renewable energy sources, and let's also assume that all these different renewable energy sources have the same share amongst each other. So, for example, PV panels or PV power plants produce exactly the same amount of electricity than, for example, geothermal plants or biomass plants. So as we said, for all the fossil power plants and also for the fossil power plants, it's quite easy. They all apply a calculation, in their calculation methods, a primary energy factor of 2.5 for electricity. but as we've seen before, we have very different primary energy factors for each renewable energy source. I had briefly explained before the approach, the option number 4, which is the life cycle assessment. And one of the basic principles of the life cycle assessment that it intentionally makes a difference in looking at what is the fossil share in the total primary energy consumption and what is the renewable share. But for comparison purposes, I intentionally summed these two parts of the total primary energy up. So fossil, non-renewable and renewable in options 4A and 4B were summed up. Okay, so let's have a look at the results. So as I said, we have an energy system where 50% come from conventional electricity. This is the yellow part in this graph. And the rest, the other 50% of final energy electricity, they come from renewable sources. And here you can see what this means in primary energy terms. First of all, you see that some of the different options, so what we did here, of course, is applying all the different options from 2A, 2B, 2C through 3, which is not that important here, but again, also the options 4A and 4B. And they all deliver very different results. So here, for example, let's take option 2A. Although we have 50% of electricity output from conventional electricity, you see that we have approximately 60% share in the total primary energy balance. On the other hand, in 2B and 2C, you can see that the renewable energy sources have slightly more than 50% share in the total primary energy balance. Also, applying this approach to options 4A and 4B would mean that we have almost 2/3 of renewable electricity share in the total balance, in terms of primary energy, of course. So, and what does it mean? What implications could this have? So let's assume we distribute the reduction of the final energy consumption evenly to all the energy sources. Then this means we have a 10% reduction of electricity use. We of course also have a 10% reduction for each energy source, so all the power plants just reduce their power output by 10%. And that of course also would mean we have a 10% reduction in total primary energy. So very easy like that. But if we have a look at the target of the Energy Efficiency Directive, the overarching target is to reduce primary energy consumption. So a question could arise that we say, from which source should we reduce supply most for maximum relative primary energy savings? So first of all, getting back, it seems to be more attractive when only aiming at maximum primary energy reductions to switch off renewable power plants rather than fossil power plants in all those cases where the renewable share is higher than 50%. Yeah, it's obviously saving more than 50% if we would switch off all the renewable energy. And in this case, for example, it would save less than 50%. So it, in this case, would make sense to look at the renewable energy sources when aiming at maximizing the primary energy reduction. So as you could see in the previous picture, switching off power plants, renewable power plants, applying options 2B or 2C would save more than 10%, although we only reduce the final energy consumption by 10%. Of course, this is quite a crazy result, and it even gets a bit more crazy when we take another example. Let's take 4A, and I would like to say that I intentionally abuse the method 4A a bit here in this case, but still you could be tempted to do so. And in this case we say, okay, if hypothetically all fossil power stations are switched off in option 4A, let's go back to 4A, this would be here. So let's switch off all renewable power stations. It would reduce final energy electricity output by 50%, but it would reduce primary energy by approximately 2/3. This you can see here. So if we switch off all fossil power stations, we have a reduction of 100% in greenhouse gas emissions, but only a 33% reduction of total primary energy use. So this would be this share here. We switch off this part, then we save 33%, but 100% carbon emissions, obviously, because we switch off all the power plants that produce greenhouse gas emissions. And if vice versa, we would switch off all renewable power stations. Again, we would have 50% reduction of electricity supply. We would achieve 0% reduction of greenhouse gas emissions, and we would achieve 67% reduction of total primary energy use. So you see that we have quite a conflict here between the greenhouse gas emission targets and the total primary energy use reduction targets. So this leads to the insight that we absolutely have to reflect on the adequate application of the different methods to avoid unintended and misleading results. For example, applying methods 4A or 4B for deciding which power plants should reduce their output in order to achieve primary energy targets. It also teaches us that primary energy only focus may lead to conclusions or decisions that clearly contradict climate targets. As we saw, a significant reduction in primary energy can have very little impact on reduction of greenhouse gas emissions. So the role of renewable in energy statistics. As I said, typically a primary energy factor of 2.5 is used. From the examples you could see if a smaller primary energy factors is used in the statistics, e.g. option 2B uses 1 for hydro, solar, PV and wind, it would make sense to replace fossil power by renewable energy sources in order to decrease the total primary energy balance. But as you can see, this only would mean indirect savings because we still wouldn't have saved a single kilowatt hour on the output side or on the energy use side. So it means replacing 1 unit of fossil electricity by 1 unit of wind effectively would save us 1.5 units of primary energy without saving a single kilowatt hour in final energy. So the impact on the total primary energy use you can see here. I will explain this example. We say we have 10 units, so it's another example, and it is about having 10 units of electricity from fossil power plants should be replaced by 1 unit of electricity from each of 10 alternative power plants which are renewably based. And then let's have a look what net change this would make applying different options. You see here that replacing fossil fuel, one unit of fossil electricity by renewable electricity plants in some cases leads to an increase in, where is the arrow? Leads to an increase in primary energy, for example here in waste, because it has a smaller efficiency, conversion efficiency. We have a higher primary energy factor for waste, so replacing the conventional mix by um, biomass would lead to an increase in primary energy. And here on the negative side of the columns, you see those renewable energy sources which have a smaller primary energy factor, which leads to a reduction. And in total, in the end, you have um, renewable energy sources that increase your balance and others that decrease your balance. And the net effect of this, for example, would be an increase of 5, and on the other hand, a decrease of 10, which switching to or using option 2A, and assuming that we replace 10 units of fossil energy by renewable energy will finally save us altogether 5 units of um, primary energy. And you see that we get very different results with the other columns. 2A, as I presented, decreases primary energy by 5 units. But for example, using option 4A, we would see an increase by 15 units. So it's especially problematic for biomass, geothermal, and solar thermal, which usually have larger primary energy factors than 2.5, because using these sources will increase the primary energy. So the Renewable Energy Directive, we take another example. We have a total gross inland consumption of 100 units of final energy from fossil fuels and another 100 electricity generation from renewable sources. And again, this generation is distributed to 10 units for each renewable energy source. So what we did here, because the target of the Renewable Energy Directive is to increase the share of renewables, is to calculate the share of renewables that we would see from this energy system, applying again these different options. And as you can see, we will, depending on the method that we apply, achieve different results starting from 30% renewable energy share with option 2A up till 55% renewable energy share in option 4A. This means that different methods can create the illusion of very different achievement levels of renewable energy targets, although these results are valid for one and the same energy system. This illustrates what I just showed before. You see here, for example, option 2A, 30%, which I just mentioned, and you can see here that when looking at the different renewable energy sources that we have here, it's summed up by very different shares of these sources. Specifically, you can see it for geothermal energy in option 2B. You can see that geothermal has a very high share because of its very low conversion efficiency that is assumed in this method. So there is a very big difference. Just looking at geothermal in this method, 2B, it has a very low share. Sorry, 2A. In 2B, it has a very big share, and then you can see the shares in the other methods. So the Energy Performance of Buildings Directive, finally, we have to deal with imported and exported energy. As I said before, you've already seen that chart. And, well, it also means that looking at this equation, it will have a very big impact on the energy balance of the building depending on which source you take. So this means depending on in which country you are, you might use very different energy sources for your building in order to minimize the resulting primary energy balance of the building. And it also might be very much depending on the method that you use, which energy system you would prefer for your system in order to achieve a balance that is close to zero. Okay, the summary on the directives. The Energy Efficiency Directive aims at improving the end-use energy efficiency, and the indicator is the total primary energy use. But we've seen that it's very problematic to use that because improvements of energy efficiency using primary energy as an indicator might occur without any reduction in final energy use, which is the basic target of the Energy Efficiency Directive. The Renewable Energy Directive, again, depending on the accounting method, we have seen very different shares of renewable sources, which means that virtual improvements in the renewable energy share could be achieved by just playing around with applying different methods. And you've seen that different countries, in fact, you've used different methods in their energy statistics, so it's not a theoretical possibility. The Energy Performance of Buildings Directive has primary energy use as the main indicator, and so again, depending on which method you apply, you will achieve very different primary energy balances for your building. The conclusions: we have some issues with the primary energy factor of 2.5. There is no unambiguous scientific value. The current conversion factor of 2.5 that, for example, is mentioned in the Energy Efficiency Directive is based on Eurostat figures that stem from approximately 2001, so there is a strong need for an update. We also have lack of consistency. You've seen that, of course, the European Commission cannot force a certain primary energy factor on the member states, and so it means that still, even having default values like 2.5, they are free to choose primary energy factors that deviate from 2.5. Then we have a lack of transparency, so not always it's clear where the primary energy factors come from because they are not entirely based on scientific arguments. This means primary energy factors on a national level should be regularly revised, and there should be a method, a harmonized method for calculation primary energy factors on a national level in order to be able to compare them. So final conclusions. Member states should use the same or a very similar methodology for determining primary energy factors. We've seen that application of the different methods that were already introduced in part 1 of this paper series will have a significant impact on the primary energy balance and also on share of renewables that we can see. We need to prevent the abuse of methods to promote different energy sources. We've seen that using methods 4A or 4B will, for example, lead to very different results compared to applying the methods which use equivalence, energy equivalence. And so, yeah, selecting the method might enable you to reach the result that you would like to have, even if this method is not really meant for the purpose. The methodology needs to be transparent and should be based on available data in order also to be able to update the values regularly. It should be based on solid scientifically based grounds for all types of power supply, and it should be commonly applied. So something like, yeah, a delegated act or something like that that may be handed to the member states might help them to base their calculations for primary energy factors on a common ground. So methods used for determining primary energy factors for energy from renewable sources must be in line with climate policy targets. And I think especially for geothermal energy, it was very clear that on the one hand, geothermal energy is a very good way to reduce primary energy, but on the other hand, it's vice versa. So sometimes there is a conflict between reduction in primary energy. That would mean, in the case of geothermal, please reduce geothermal in order to increase in order to decrease primary energy. Sorry, that's a bit complicated. I'm a bit confused myself, so I start from the beginning. Having a look at primary energy, we could recommend please reduce geothermal energy because it produces a very high share of primary energy, and leaving out geothermal would lead to a very strong reduction in primary energy. So in this case, you might say, okay, please reduce geothermal energy in order to reduce primary energy. But we also saw that geothermal energy has a very high share or contributes to a very high share in renewables. And so here we would have the contradicting recommendation, please increase geothermal energy in order to increase the share of renewable energy. So this is the final slide. Changes in the power system which lead to reductions in greenhouse gas emissions generally should always lead to reductions in primary energy use. So as I just pointed out, this is problematic when we use total primary energy, and sometimes we get contradicting results that switching from one energy source to the other reduces greenhouse gas but increases primary energy use, and it shouldn't be like that with renewable energy sources. What we've also seen is that reducing primary energy doesn't necessarily mean that we actually reduce final energy. So the balancing methods that we use should allow us to clearly make a difference between direct primary energy savings stemming from actual final energy savings, but also see which of the effects can be attributed to indirect primary energy savings, which simply come from changes in the energy mix. This means by replacing one energy source by another. Then renewable energy sources should be treated equally relative to their effect on reducing greenhouse gas emissions and the calculated share of renewables. I explained with geothermal energy that very contradicting results may occur, but I think with renewable energies, we clearly should always have the same direction, because in the end, we have overarching climate targets, and helping them should also give us a reduction in primary energy and not only in carbon emissions. And finally, it doesn't seem helpful for achieving a well-balanced mix of different renewable sources when one zero-emission source, so one renewable energy source, is outpaced by another zero-emission source because it has a very different primary energy factor. So that's also an issue that needs to be solved because, as I said, in some cases, applying some of the methods, it seems to be more attractive to have one renewable source than having the other source because it seems to help more in achieving primary energy targets. And this finally tells us that, well, relative to achieving greenhouse gas reduction targets, it's very problematic to heavily rely on primary energy factors only. So we need a better balance here and a bit more scientific ground. Thank you very much.